Welcome to the second video on unsymmetric bending. In this one, we'll look more closely at a specific cross-section, and we'll determine our equations that we'll use to determine the stress due to unsymmetric bending and the location of the neutral axis. The stress due to unsymmetric bending will be this equation right here, and the location of the neutral axis will be given by that. When we have a section subject to some moment about some arbitrary direction, let's just say it's like that, moment about that, we can of course break this down into two moments, two component moments, one about the x-axis, or I guess the z-axis, and one about the y-axis. And that means, and the components for this will be, well, let's use the same colors that we used before. Isn't that fun? That the moment in the y direction is going to be equal to the total moment that was applied times the sine of this angle right here. So let's draw that in, and then we've got that, and that'll be, oh gosh, no space. Anyway, that will be, we'll call that one phi, I think, yes, and then the moment in the z direction will be the cosine component of that. And with these in hand, we can now write our stress equation. So assuming that we are able to determine the second moment of inertia about the y-axis and the z-axis, we can write that our normal stress in the x direction is equal to the stress from the moment about the y-axis plus the stress from the moment about the z-axis. So that's going to be the moment about the z-axis divided by the second moment of inertia about the in the z direction times our lever arm in the y direction, right? So if this is our z direction, this blue one, then the farther we are in the y direction, that's going to be increasing our stress. Ditto for the y direction, we're going to have the moment about the y direction divided by the second moment in the y direction, and this one is going to be times our distance to the left or right, in the z direction. So this is our normal stress due to moments. So we can just do basically what you probably would have done if I hadn't told you what to do at all. I assume most of you would have just busted this down into components and then summed it all up. That's certainly the easiest approach. But if we want to find the neutral axis for this, then what we're going to have to do is we're going to have to say that at the neutral axis, the normal stress due to bending is 0. And if that's the case, then we just have to to sum these two things together to get 0. 0 is equal to the stress due to the moment about the z-axis plus the stress due to the moment about the y-axis. Right? So that's going to be y times z. And then we can also, if we plug these in, these two things in, we can go ahead and rearrange this as y over z. That's going to be our location. So y divided by z is equal to I z over I y times the tangent of phi, the angle that our moment is at. Now, I guess there should have been a negative sign in front of all of these, right? So now we've got this, and that is going to equal y over z. So we can say that that is equal to tan, we'll call that theta, where this is the direction of our neutral axis. So if we've got this, then we're going to have, let's draw it nice and fat and head on. 12, perfect. So if this is our cross section, then we're going to have some angle that our moment is applied at. Let's draw that like this, and then, you know, and so this right here could be the angle that our moment is applied at. But then we'll have a different value, a different angle. We'll also go through our neutral axis. And this one would be theta, the angle of our neutral axis. So this would be our neutral axis right there. See, they're not perfectly lined up, but they are pretty easily related to one another as long as we know the second moment of inertia about both the y and z axis, and because you know, that's because we're allowed to look at it like this. That's pretty easy to find. If we were trying to look at this like at this angle, it'd be kind of tricky maybe to find the second moment of inertia, especially if we didn't have the ability to make the thin-walled assumption, which is the only thing that makes finding second moments of inertia a fun activity in calculus and not terrible frustration. So let's just do a nice quick example with a nice simple cross section.